one of the mysteries that eludes me still here at CFA is what the official actual start time is for a CFA event. The Boston Symphony always starts 5 minutes late, so we should, even 5 minutes late, I guess, is okay. Anyway, it's a great pleasure to have with us Marta Volonteri today. She's our Stephen Murray Distinguished Lecturer. Her professional career has taken her from a long list of places, which I'm going to have to read to you. She began at the University of Milan with her PhD in 2003. She was a postdoc at Santa Cruz. She then went for a research associateship in the other Cambridge, not here. She was an assistant and associate professor at the University of Michigan. And since 2012, she's been the director of research at the IIT in Paris. So when planning her visit, she had, I guess, an email negotiation with Akos to make sure that she didn't come here in what she described as the heart of Boston winter. And I can tell her that we've arranged for her an exquisitely beautiful day. It's almost summer. So she can go out and walk and enjoy herself here. It's a beautiful day. Anyway, her research interests focus on a wide variety of extragalactic topics. You can see some of them on the slide here, but include AGN all the way up to cosmology. She's very well known for studies in supermassive black holes, their formation and evolution. And her title of her talk today is Growing Black Holes in Growing Galaxies. And I'll give you Marta.
Thank you very much. It's really a pleasure to be here in this fantastic springtime. And also, I realize it's the week before the Chandra deadline, so I understand that most of you will be busy, but if you want to talk about proposals, I can work with you. Anyway, so today I want to discuss with you a few thoughts, ideas on the first black holes and their growth over cosmic time. I will focus mostly on the first billion years of the universe. And this is work in collaboration with many collaborators, but in particular with Mélanie Abouzi, who is a PhD student at the Institut Astrophysique de Paris, and she's working on the first black holes in cosmological simulations. So let me start with a brief introduction on our black holes, on our favorite black holes. Here we have stellar mass black holes that are all the rage now after discovery, well, the detection of gravitational waves. These are, for my standards, very tiny, small black holes. Therefore, they have masses less than a few tenths of solar masses, and we know pretty well how they formed and evolved, which is through the evolution of massive stars. Now, these black holes are very interesting, but these are not what I focus on. I mostly work on massive black holes, massive and supermassive black holes. They were first proposed once quasars were discovered about 50 years ago as the central engine of quasars, and nowadays AGN also of lower luminosity. This is a nice image of M87 with the jet coming out of the center. So you see here, these black holes inhabit the centers of galaxies of different varieties, from small to large, and I will discuss a little bit about that. And in general, today, in the current universe, in the local universe, these massive black holes have typically masses larger than 10 to the 5 solar masses. And I will discuss a little bit the connection between the different ranges in the masses that we see. Now, as I said, supermassive black holes were first proposed as the engine of quasars, so very active objects. The luminosity of a quasar can be 10 to 11, 10 to 13 solar luminosities. But then we have a completely different type of objects, which are quiescent black holes. The best example that we have is in our own galaxy, the Milky Way. This is a radio image of Sagittarius A star, highlighted here in the center. Now, if you take the luminosity of this of Sagittarius A star, where we know by stellar dynamics, by the measure of the orbits of stars, that there is a black hole with a mass of about 4 million solar masses in there, the total luminosity you get is 10 to the 34 ergs per second, pretty much the luminosity of our own sun. So we have the two extremes of quiescent black holes, such as our black holes, with the luminosity of a single star, comparable to the luminosity of a single star, and quasars with the luminosity of entire galaxies. So black holes that have similar mass can have a huge difference in luminosity, but we will see that black holes have not only different luminosities, but also very different masses. So for a sample of about 90 galaxies nearby that are hosting quiescent black holes or very, very low luminosity AGN, it is possible to measure the black hole mass in the center. This mass is shown here as a function of the bulge mass, the mass of the central spheroid, stellar-dominated spheroid of the galaxy. This is a compilation of data from Corman and Ho 2013, where I just plotted all the points that are available at that time, so almost 3 years ago now. So the point here that you see that first, the masses span a wide range from 10 to the 6 solar masses to a few times 10 to the 10 solar masses. You see here that black holes inhabit also galaxies of different masses. But in general, you can see that there is a trend here. I'm not going to spend much time talking about this correlation or the tightness of the correlations, but I would say that in a simple way, we could say that small black holes live in small bulges, big black holes live in big bulges. For what I'm going to discuss today, this is sufficient in terms of what we believe about the connection between galaxies and black holes. And I read this as, since small black holes live in small galaxies, big black holes live in big galaxies, this means that somehow, these objects evolved at the same time. They co-evolved as a function of time. Interestingly, the stellar populations of bulges, of stellar bulges, are pretty old, several giga-years old. So we expect that really this joint evolution, this journey of galaxies and black holes also followed a long evolution over several billion years. So these are all very local galaxies. The Milky Way is also there. But then we can go to the other extreme. As I said, supermassive black holes were first proposed as the engine of quasars, and also today we can use quasars as a signpost of the farthest black holes. This is a compilation of quasars at redshift higher than 6 by Wu et al. 2015. Here you see the volumetric luminosity and the black hole mass. So if you focus on the masses of these objects, you will see here that are very large. In fact, if you compare them to today's black hole, the range of masses 10 to the 8 to 10 to the 10 corresponds really to the upper end of the black holes that we know today. Here I extended a little bit the figures here. So first of all, here I'm plotting black hole mass as a function of velocity dispersion of the galaxy. It's very similar to the bulge mass. It's an indication of the depth of the potential well within which the black holes live. And I added a few objects. And here we're really going into the realm of dwarf galaxies. So at high redshift, what we can detect are very massive black holes powering very luminous quasars. But then if we wait 12 billion years from redshift 6 to today, we have a population that you see extends to very low masses. I think that the current record holder is a galaxy, a black hole with a mass of a few 10,000 the mass of the sun. And then you have also galaxies like M33 or Samine or Fornax or NGC 205, where there is no black hole at all. So we have some sort of conundrum here. At high redshift, we detect very massive black holes wearing luminous quasars. At low redshift, where we are expecting to see mature galaxies, we're able, actually just because of observational constraint, to see that the lower end of the black hole mass function presents also a huge variety. So this is, as I said, these are the high redshift quasars that we have, but what if we go to lower luminosity? Can we find lower mass black holes? Well, the searches for the moment have been rather inconclusive. They have been carried in two different ways. They're looking for point sources in deep X-ray fields, for instance, the Chandra field south, and I would say that we have only a few candidates, but none of them is confirmed. And the stacking of Lyman break galaxies with photometric or spectroscopic redshift higher than 6 also led to no detection in X-ray, meaning that if there is a black hole there, it's very quiescent, or it's sufficiently quiescent to have a luminosity in X-ray less than 42 arcs per second. So at the moment at high redshift, we really have a very biased and limited view of black holes. And well, what I've been working on for the past few years, having a lot of fun, I have to say, is to try and study how black holes and galaxies evolved from the early universe to today, growing either together or in some sort of disconnected way. For instance, in this case, the galaxy grows first and the black hole catches up, or vice versa. I'm a theorist, so I use different techniques from analytical to numerical simulations, and I just want to show you and share with you some of the results that we had. So let me start with the very early times. Now, what I tend to say is that there is no black hole theory. You don't have a galaxy and all of a sudden the theory goes there and says, black hole here. You have to use physical processes to understand how black holes formed in galaxies. And this is a compilation where I collected as many proposed models of black hole formation that I could find. Let me start here by what you see at the bottom here, inflationary black hole and cosmic string loops. These are models that form black holes without requirement that there is a galaxy around it. So either black holes forming after inflation, there is a very small range in masses allowed here, or cosmic string loops. Don't ask me about that, please. I collected literature that predicts that black holes can form very massive, 10 to the 6 solar mass and higher in very early universe. Now, as I said, I'm not really going to talk about that, mostly because I'm not very familiar with the concepts. I will focus on the mechanism that have to do with the baryonic physics, with the interaction between dark matter, gas, and stars. So here I said is a compilation of models. On the x-axis, you see the black hole mass at birth, and on the y-axis, you have metallicity. I'm not going to discuss, like in a shopping list, all of these models, but just the basic physics behind it. So you see here first that there are different masses from the very small black holes. These would be the remnants of the very first stars. In some sense, they're the simplest process we can think of because they just follow stellar evolution in the same way that we know today stellar mass black hole follows stellar evolution. And then we have more exotic models where black hole seeds can form either by mergers of other black holes or by mergers of stars that form a supermassive star, or by some dramatic collapse of gas that forms all of a sudden, very rapidly, a supermassive star. In all cases, you see that the masses are something like between a few hundred up to, if you are optimistic, about 1 million solar masses. Now, you see here, I discussed the x-axis here, but you see here that on the y-axis I put metallicity. Now, in some sense, metallicity is useful because we can think of it as a cosmic clock. Metallicity increases as a function of time as stellar evolution pollutes the universe. But why is it so important for black hole formation? Well, the main reason, and again, I think I'm talking to astronomers and also physicists here, so you know that when I say metals, this is what I mean. So I think this is given for granted, but just to remind you. So why is metallicity so important for black hole formation? Well, it's not important. It's important because it determines the fate of a given star. So this is a very nice figure from Hager et al. A few years ago that shows the remnant as a function of the initial mass of a star at different metallicities, from metal-free to solar metallicity over here. And you see that there are huge differences. In particular, if you want to form a black hole, a massive black hole, as massive as you want to form this black hole, you want to look at the case where you form directly a black hole, shown in black here. You see there is a nice range of masses here, 216 higher, where a star ends its life with a direct collapse into a black hole, losing only about half of its mass. Now, this is not the same at redshift zero. At high metallicity. At high metallicity, you have much higher opacities. So the winds during the let's say red giant phases blow away a large fraction of the mass of the star. So the final remnant is not a massive black hole. And you can see here how really the probability of having a massive black hole decreases as the metallicity increases. So the link between metallicity and black hole formation has to do with the requirement to have a massive star that collapses into a massive black hole. If you pay attention to the models that I showed you earlier on, there are a couple of models that don't have any mention of supermassive stars, and in particular those that start with black hole mergers. If you take stellar mass black holes and you merge them together to form a more massive one, there is no requirement for the metallicity to be low, so this could happen throughout the cosmic history. However, all the other models that I discussed require some sort of intermediate phase of supermassive star, and in this case, you want to focus on the very early universe. So that's why we think that the first black holes formed in the first galaxies. This is just a small simulation showing you the enrichment of a given volume. So you see here in purple the explosions of supernovae, and the purple highlights the regions that are not metal-free. So once you are in a purple region, in principle, you cannot form a black hole there. So in a bit more detail, here we see a simulation. This is a 10 megaparsec simulation with relatively high resolution, 40 parsecs. And you see here the gas density and the gas metallicity. And you can follow these circles that show, let me go back again, that show where black holes form. They form pretty much at the beginning where there is no metallicity yet, but soon after the region starts forming stars and metallicity becomes too high for black hole formation. So there is a very subtle balance between the enrichment of the universe that is caused by galaxies forming stars, but these galaxies are the same galaxies that we want to form black holes. So this means that we have to be careful in seeding galaxies with black holes. It's not that black holes pop up everywhere where the black hole fairy uses her magic wand. In fact, black holes form only in some of the galaxies, in some of the halos, and not all of them. So here this figure compares the mass function of halos in the same volume that you just showed seen in the movie. In black you have the total mass function at redshift 10, 8, 7, 6. We're talking about the high-redshift universe, very tiny halos. The typical masses of these halos are 10 to the 8 to 10 to the 10, compared to the Milky Way today, which is 10 to the 12 solar masses. So these are very tiny little galaxies, comparable to dwarf galaxies today. And okay, so the blue curve below the black one shows which of these halos are eligible for black hole formation that meet all the requirement of having low metallicity, very high gas density, very high star formation, where black holes can form. And you see here that the two curves touch each other at the high mass end, but not at the low mass end. This means that massive black hole formation is a biased process. You tend to form black holes in the most massive halos, but not in the small ones. And of course, there is an evolution as a function of time, then these galaxies will merge together, so it's not a done deal. But clearly, there is a very, very, very strong interplay between how star formation and black hole formation occur in the high-redshift universe, telling us which galaxies can or cannot have a black hole. Now, let us assume that we have this population of black holes, but we don't have yet much information about what we can see. Now, this is just the number of black holes as a function of time. Well, at this point, we start with initial conditions, we start with the first black holes, and then we want to grow both the galaxy and the black hole, first to reach a population that meets the requirements of being like the population that we observe, but also making predictions for what we can see and perhaps put constraints on how the first black holes formed and grow. So at the moment, if we want to connect our theoretical models to observations, we are in a very tight spot. As I said, we have a very limited view of the high-redshift universe. The quasars that have been observed at redshift 6 and higher are about 50 by now. It's not a small number, but they are all very luminous. The typical luminosity is larger than 10 to the 46 ergs per second. So they are really bright systems to be detected at redshift. They have very large masses with some record holders. There is a black hole at redshift 7, the farthest black hole known today, with a mass of 2 billion solar masses, and a black hole at redshift 6.3 with a mass of 10 billion solar masses. I mean, 10 billion solar masses is really a lot. If you think about it, it's pretty much the mass in stars of the Milky Way. So it's an enormous object at very early times. Now, much work has been done in the last few years about explaining the growth of these black holes. In fact, you can show with simple arguments that if you believe in the Eddington limit, I do not, but you're free to believe in it. If you're limited at the Eddington limit, to explain the masses of this and the redshifts of these two objects, you have to accrete at the Eddington limit for the whole time, starting with a seed mass of about 300 solar masses, or if you start with a very massive seed, 10^5 solar masses, which really is towards the upper end of what we can think we can form in a galaxy, you have to accrete only for about 60% of the age of the universe at redshift 6 or 7. Now, this is not what I'm going to talk about. There has been already much work done on this. Tiziana Matteo, Deborah Sijaki, Anne Dubois, Tiago Costa have really done a lot of work in this field. I want to focus on something different. I want to focus on the small objects, on the normal ones. I always say that if we just study these black holes, it's like if an alien comes to Earth and picks a basketball player to try and understand what is the typical height of human beings. It's not a good example. What I want to know is about the population of black holes. However, for the population of normal black holes, it's, as I said earlier on, observationally we are not in the best situation because we don't have many detections yet. But being a theorist, I can create my universe in my computer and then hope that the observers will be able to find the signatures. So my question, what I want to discuss today, is really where are the normal black holes at high redshift? So the high-redshift black holes that we see today, those powering the high-redshift quasars, are really the tip of the iceberg. They are in very biased, dense regions. They're really not the typical object you should follow. So what do you expect for normal black holes in normal galaxies? These are the black holes that we need to explain the black hole in the Milky Way, which is something that we know is very nearby, which is something that we know has a mass of 10^6 solar masses, not 10^10 solar masses, so it cannot have been born from the high-redshift quasars. Now, if we look at the mass function of black holes at formation from the simulation that I showed you earlier on with all the seeds popping out here and there, this is what we find. So at birth, black holes are pretty small, about 1,000 solar mass, giving and take an order of magnitude. These are tiny. These are normal black holes. I mean, if you take a 10 megaparsec cosmological volume, you expect to find the Milky Way in there. Not a cluster of galaxies, but this is what we want to explain. Now, here we're talking about low-mass black holes, about 1,000 solar masses, in low-mass galaxies. I showed you earlier that the mass of the halo is 10 to the 8 solar masses. The mass of the galaxy inside it is even less. These are what I call fragile environment. These are galaxies with very shallow potential wells. In fact, the binding energy of the halo is not much more than the energy that you have when you have an explosion of a supernovae out there. So this is an evolution as I said, in what I call a fragile environment, where supernova feedback, where supernova explosion have a dramatic impact on the thermodynamics of the gas in there. Now, the same gas that you have in a galaxy is used for star formation. Well, it's being also recycled. And then you want to use it also for black hole accretion. Now, if you have input of energy, kinetic and thermal energy from supernovae, you are changing the properties of this gas. And the gas will become more diffuse and hotter and will be less likely to condense in the very center while the black hole is and feed it. In fact, what we find is that when we include carefully supernova feedback in simulations, the growth of black holes is suppressed. This simulation run by Anne Dubois. It's a cosmological simulation. It's a zoom. You see here various redshift from redshift 4.7 to 3. It has a very high resolution, 5 parsecs, meaning that for most of the time we can actually resolve the sphere of influence of the black hole. We can see the gas that flows in and out towards the black hole with very high accuracy. And you see here many young stellar population, these blue stellar clusters where stars form, and these stars will evolve as supernova in about a few tens of million years. And this supernova is energize the gas in the galaxy and make it possible for the black hole to grow only in spurts. You see here as a function of redshift, the Eddington ratio, the let's say the specific accretion rate of the black hole. And you see here that for most of the time, after redshift about 3, this black hole is not doing much. It is trying, it would love to be eating some gas and grow, but it simply cannot get to very high accretion rates because the gas is flowing in and out because of supernova feedback. Once we get to redshift about 3.5, the galaxy is massive enough, the potential well is deep enough to retain the gas despite supernova feedback. And at that point, the black hole starts growing and happily grows all the way to redshift 2.5. Now, this is just one simulation. This is one galaxy, very high resolution, but it's just one galaxy. So is this a common feature or not? So this is what we're doing with a different set of simulation. Again, this is the same movie that I showed earlier on. You can form black holes in your cosmic box, and then you let them grow. How do they grow as a function of time? I will show you in a minute how the population of black hole evolves as a function of time in that volume. As in, this is a very small volume, 10 megaparsecs, so it's just the local volume, the local group pretty much. But again, at very high resolution, what we want is to study the physics that is feeding black holes, is feeding stars, and feeding all this circle between galaxies, stars, and black holes. So here you will see the formation. Black holes will appear when they form and then they grow. You start from a dark red at earlier times, and then you get to red at late times. So you see here at high redshift, the black holes start forming, and then eventually they grow. Notice here how this evolution goes. The galaxies tend to grow a bit faster than the black holes do. This is the same that I was saying earlier on. Black holes tend to be stunted in their growth when they are in very shallow potential wells. This is not the same for stars, although stars are suppressed too. Black holes really require very high density gas in the very center of the galaxy, in a very small region. So they're a bit more picky about what they eat than star formation that occurs throughout the disk. So here we are comparing the growth of these black holes to observations at redshift 0. So beware, the simulation stopped at redshift 3. The observations are at redshift 0. But what we are seeing is that the population of black holes evolves, but slowly, only when the galaxy becomes massive enough to retain its gas, despite supernova feedback, we see that black holes start growing and become sufficiently massive. The fact that I just want to prove you very quickly that it is supernova feedback that does the trick. This is the same simulation run with a much weaker supernova feedback. A supernova feedback that actually does not reproduce observational properties of galaxies, but this was just a thought experiment to see, to make sure that what we're finding here makes sense. And we see here that the evolution of black holes is very different. Black holes become very massive very quickly. Black holes over here accrete at the ending rate for most of the time. But as I said, this simulation does not reproduce observational constraints. So we believe that black holes have a very hard life at the very beginning until they can grow and become more massive. So this was a theoretical effort. Does it make sense in any possible way? Well, I prefer to compare my models to observations whenever possible. And at the time, I think that the best observations that we have for the relationship between black hole mass and galaxy mass at high redshift, 5.7 and higher, is this. Here, the black hole mass is estimated. It's not measured, it's estimated through a single epoch spectroscopy. You basically use the virial theorem. And you use the virial theorem also for the galaxy mass. These are ALMA observations, meaning that what you measure are the properties of cold gas in a galaxy. And assuming that this gas is in hydrostatic equilibrium, knowing the size of your galaxy and the velocity dispersion of the gas, you can estimate pretty much a galaxy mass. It's an estimate, it's not a measurement, but it helps us. Now here in gray, you see the relationship between black hole mass and bulge mass at redshift 0 with its expected scatter. And all the points represent quasars at high redshift. So first you see that high redshift, you seem to have a larger scatter. And most black holes, especially out here, appear to be much more massive than expected. Now, I just told you that black holes have a hard time to grow at the very beginning. Well, I was not focusing on these black holes, but can we reconcile these two? Are really black holes overmassive at high redshift? Have I just made a mistake with my simulation, which could be, by the way, but I don't. I want to test this first. So the rule of thumb is that if you measure black hole masses, or if you estimate the black hole masses and the galaxy masses for redshift quasars, you obtain something that is overmassive. The black holes are above the relationship today. So you can do a simple experiment. You assume that there is an intrinsic correlation between black hole mass and galaxy mass, just an equation, whatever you prefer. I chose the one that reproduces the results at redshift 0. And then we can take the galaxy mass function that we know at this point out to redshift 7 with uncertainties, but we have something there. And then by convolving the scaling between black hole mass and galaxy mass and the galaxy mass function, you can find the black hole mass functions and all the properties that go with that. So the procedure is as follows. I take the relationship between black hole mass and stellar mass at redshift 0. Here you see basically two broad distribution of points. The blue ones, these are dynamically measured black hole masses in mostly bulge-dominated massive galaxies. And in this case, the black hole mass is roughly 10 to the minus 3 the mass of the galaxy. And then you see here some red points. These red points have the galaxy mass and the black hole mass measured. These are AGN, so the black hole mass is estimated, again, through the virial theorem, and the galaxy mass is measured through, in the same way as the blue ones with a color correction. And in this case, for this galaxy, these small, low mass, disk-dominated galaxies, the black hole mass is roughly 10 to the minus 4 the mass of the galaxy. Now, if I take this and I convolve it with the galaxy mass function, here I show the mass density in stars. So it's the integral of the galaxy mass function at different redshifts. You have here different surveys, and you see that at low redshift there is typically very good consensus. At high redshift things are much more uncertain, but I mean it's always high redshift. Now, if we take this and we convolve with your favorite correlation, my favorite is the red one in this particular case, because at high redshift I'm not looking at very massive old ellipticals, but I'm mostly looking at small disk-dominated galaxies, or anyway, not spheroids. This is what I obtained. So this was the stellar mass density, and this is the black hole mass density as a function of redshift, pretty much the same redshifts, once you convolve with these correlations. The blue curve here is what you get when you use the blue correlation, the vanilla correlation I called it, and the red is what you get when you convolve with the red correlation. And and here it's compared to all the limits. Mostly we have upper limits at high redshift from the known detections in the Hubble, in the Chandra deep fields. And you see that if black holes are really as massive as they are today in galaxies, you tend to overpredict pretty much everything. So you are not in the range of observed, in the range of the upper limits. So if you compare then if you take this convolution and you compare it with the black hole mass function shown here in green that you obtain from the AGN luminosity function at redshift 6 by Willott et al. Assuming a given Eddington ratio and active fraction, you actually find that the red fit works pretty well for the same for the AGN as well for the quiescent galaxies. Now, here you should stop me and say, but this does not make sense. So here the red curve says that the black hole mass is 10 to the minus 4 the mass of the galaxy. I showed you earlier that from the ALMA observation, the black hole mass is more like 10 to the minus 2 the mass of the galaxy. So what's going on here? So here I put something that is within the error bars, actually very, very, very well. Works out, but the averages are wrong. This is just a bias, observational bias that was highlighted by Todd Lauer back in 2007. If you start from a given intrinsic correlation, this is the intrinsic correlation that I just showed you, the red one with black hole mass 10 to the minus 4 the galaxy mass, and you have this as a total correlation. Then if you select only objects that meet this criteria, luminosity higher than 10 to the 46 ergs per second, this is what you see. So if you want to have basically you're picking the basketball players of the black holes. You're picking the most massive black holes at a given stellar mass. So having low mass black holes not growing rapidly because they have trouble with the shallow potential wells is not in contrast with having some of the black holes growing very fast. And they can all be part of the same family, meaning the same intrinsic correlation. So in summary, I would say that abnormal black holes in normal galaxies are those that can explain the high-redshift quasars that we observe today. Normal black holes in normal galaxies may grow slowly, but hopefully can still be detected. So this is just, I will finish here with just a prediction for the future. This is the prediction for the luminosity function of the simulations that I just showed you. Nicely they connect, so the simulations are shown in red, and in yellow you have the observations. Nicely they connect to what we see today, but they go obviously to much fainter luminosities. And here with Francesca Civano, we calculated how many of these objects, how many of these faint AGN, tracing the real population of black holes we can see at high redshift. And you see here that with very sensitive and large area instruments, we can hope to detect many tens of these small black holes, even at high redshift. These are all objects at redshift 6.5. So I will not discuss the galactic archaeology. I will just finish with a couple of pretty pictures. As I said, I focused on low-mass black holes at high redshift. Low-mass black holes exist also today. These are some of my favorite galaxies that are tiny dwarf galaxies hosting black holes in their center. You can highlight as AGN, like in this case, the AGN is very clear, or in this case. So the future for understanding black holes and galaxies, in my opinion, is to look at the small objects, the small black holes, and this is where I will leave you with. The physics of massive black hole formation and growth is what tells a galaxy if it can or cannot have a black hole, despite the black hole theory. And really, black holes at the low mass end are those that we have to study to understand the early growth of black holes. I focused on high redshift today. I just showed you, in a glimpse, the three dwarf galaxies that we have at low redshift with black holes. And I think that many people are looking at more and more black holes in dwarf galaxies to help us understand and disentangle the growth of black holes from the formation of black holes. And perhaps even seeing if the correlation between black holes and galaxies are in the eyes of the beholder or they're real. And I will leave you with a movie. Thank you very much.
Thank you, I don't know whether there's any light.
You just have to turn it on.
Ah, sorry.
You must see. Or this.
Okay, fine. Comments and questions, anybody?
I have a comment. So one way of looking at this is that the black holes all grow slower than about 1 solar mass per year, right? Whereas galaxies grow faster than that. So, but the black holes are inside the galaxy. So you can look at the galaxy as a kind of machine which prevents gas that's coming in from outside from actually getting down into the black hole. And that happens by a variety of processes, the supernova being one of them, but there are also stellar dynamical processes which will prevent that infalling gas falling onto the galaxy from outside from actually getting down into the middle.
Yes, absolutely. I mean, I focus on this very tiny galaxy at very high redshift, where perhaps supernova feedback is the main culprit, but it's definitely not the only one. I completely agree with you. And the reason why I studied high redshift is also because it is a bit easier. More and more processes pick up at later and later times, and the studies become more complicated. So I completely agree. Oh, the white points there are all black holes, by the way.
They're emerging.
Go ahead.
So I asked this question to John Carmody when he gave a colloquium. So where are those black holes in M33 and NGC 205? Well, John Carmody always said that M32 is sort of the normal elliptical galaxy, which I don't agree, by the way. But if you look at M32 and NGC 205, they have identical stellar masses. But one has, what it is, 2 times 10 to the 4 times 10 to the 5?
I have it in a
or whatever,
plot.
yeah. And the other one has
no black
the
hole.
upper limit of 2,000. So where is it?
Well, are you asking if there is one or where it is?
Yeah, I mean, if there is one, or where, if there is no, were there ever? I mean, like,
Well,
maybe it lost it during some merger event.
for a dwarf galaxy, I think that losing black holes is a bit unlikely because you need to have a merger with another galaxy with a black hole as well. So I would say that probabilistically, as you go to dwarf galaxies, it's more likely that you have never formed a black hole to start with. As I said, there is a very complicated interplay between gas, stars, and metallicity, metal pollution that determines whether a galaxy is eligible for black hole formation or not. So two galaxies that today look exactly the same, maybe one formed stars a little earlier on than the other one, and one was eligible for black hole formation or not. So what we're trying to do with these simulations is actually to bring them to redshift 0 and exactly study what do the galaxies that do not have a black hole today look like. Is there any telling sign or not?
Can the fact that NGC 205 has 1 billion-year-old stellar population tell you something? Compared to M32, which is like 3 to 4 billion years.
I think it's very important because the time when you start forming stars tells you if you can have a black hole or not. On top of my head, I cannot answer right now. But as I said, if you want to form black holes going through any stellar evolution phase, you really have to pick very low metallicity systems. So when the galaxy started forming stars, where it was, if it was in a metal-free environment or the neighbor had polluted it, it's very important. So stay tuned. When my student finishes the PhD, perhaps she has an answer. This will be October.
Martin? Oh, Francesca, go ahead.
So this is maybe more like a question I'm trying to think. Like we know that all your works cover redshift 8, but we know that galaxy mass function up to redshift 10, and last week was set the record
Yes.
to 11.1 for the highest redshift galaxy. So is there any? Are you planning to move to higher redshift, or you wait for the observer to detect more redshift?
Well, if I can go back to this figure here. So here you see this is the mass function that we have at high redshift. It is true that the samples are building up, but at redshift 7, between this measurement and this measurement, there is about an order of magnitude difference. So when I was working on this, I felt that the ground was a bit shaky, so I think this is a bit of a speculative work. At redshift 11, we have at the moment 1 galaxy. So, I could fit anything I want with that. So I think, so I'm doing...
Maybe there are unders between 8 and 10. So
If there are enough that I can put an error bar, then I'm happy to work with them. But I'm waiting for the error bar first.
So you mentioned in passing that the bulge is old,
Mm-hmm.
and you have a bulge-black hole mass relation. I hadn't really thought about that before. Does that push the epoch at which that relation was set up back to some interesting redshift, like beyond 2?
No, not much. Also, this is the other problem. I kind of mentioned this, but not much. So there is a black hole bulge correlation that seems to be rather tight, although we can discuss about this for 3 hours. And then here inside, this is not bulge mass, this is stellar mass. Why do I like stellar mass? Only because it can be measured at redshift higher than 0. But you see here that there is a very broad distribution. So This is telling us something perhaps about when the correlation started. The ages of the stellar population in bulges would say that it's redshift 3 or so, which is not that much. At redshift 3, the direct observations of the relation between black hole mass and stellar mass, it's not bulge mass by redshift 3, but redshift 2 or 3, cannot tell at the moment whether there is an evolution or not of, say, the ratio between black hole mass and stellar mass because of the biases that I just discussed. Todd Lauer was the first to discuss it, Andrea Merloni and all. But I would love to see, if this is true. If you go to redshift, in simulations, I can tell you, we see a difference between redshift 4 and 3. Do I believe it? No. I think it's... not in this simulation. In these simulations, we don't actually, but in large-scale simulations where you have a less detailed description of the physics, we see these changes, but I'm not sure they're real or not. So, again, if theorists and observers walk together, no. Yes, I like that.
Yes, I was kind of intrigued by that movie you showed, because if I assume that is the Milky Way, that basically would imply the Milky Way has like 5 or 4 supermassive black holes. Basically, we have one in the center, but there must be more.
Well, that was actually a dwarf galaxy. It was smaller than the Milky Way.
So what is the, for example, in the Milky Way, would we expect like 10 to the 5, 10 to the 4 couples?
Okay, on top of my head, it depends on the assumptions of the models. But yes, you do expect, I think, a few black holes per Milky Way. These would be low mass black holes. Typically, they are stranded in the halo, so there is simply no hope to see them. But the prediction of models of black hole formation in hierarchical structure do predict the presence of these black holes. As I said, it's very hard to observe them because typically they're very far away with luminosities less than 10 to the 36, 10 to the 39 electrons per second, because they're in diffused hot gas, if anything. Gravitational lensing is not ideal because if you look for the macho periods, the masses are too big, so you don't see the periods. So there is a clear prediction. I cannot tell you how to observe them, but there is a clear prediction. For a few, and the number of these stranded black holes increases as the galaxy and halo mass increases.
So what is the next massive one typically? Is it like an order of magnitude less, so we have a 10 to the 6 in the center, so we expect a 10 to the 5?
It doesn't scale with the mass of the black hole. It scales with the mass of the halo. So it scales with the number of mergers that you had with other halos with black holes. I have a plot that I can show you later.
Anybody, any questions upstairs? No? Alexei?
So you kind of discounted these giants at redshift of 7 as abnormal basketball players, but what would be the evolutionary cost at least to 10 to the 9, 10 to the 10?
Okay. This is my particular version of it. I'm not a believer in the Eddington limit. I don't believe in the Eddington limit. So if you are open-minded and you allow for accretion to occur above the Eddington limit, I'm talking about the accretion rate being above the Eddington limit, which doesn't necessarily mean that the luminosity is above the Eddington limit. Then building these black holes is not crazy. And if you take these simulations and you just calculate, you close your eyes and you just say, how much gas do I have there? Can I feed the black hole at super Eddington rate? You find that about 10% of all black holes at redshift 6 and higher are fed for at least a time with an amount of gas that is way above Eddington. Now, my point is, the galaxy is giving to the black hole a solar mass per year. The black hole is 10 to the 5 solar masses. This is way out, way over the Eddington limit. What does the black hole do? Sorry, I don't like this too much. Can you please come back later with less mass? And that is a matter of the physics of accretion disks. And there are several models that say that you can have an accretion rate that is super Eddington on the disk, and then the black hole can accept part of it. So this is in my opinion, we should just not think of the Eddington limit as a hard limit anymore.
So does this happen when the black hole is still low mass, or is it approaching?
It is easier to have it when the black hole is low mass because you need So for a 10 to the 8 solar mass black hole, the Eddington limit is about 1 solar mass per year. So if the galaxy gives 1 solar mass per year at a 10 to the 5 solar mass black hole, this is super duper Eddington. Also, angular momentum plays an important role that I don't think has been appreciated in the galaxy, not in the accretion disk. That has been studied, but it's not been appreciated yet. But I think it would be easier for when the black holes are low mass than rather than when they. I mean, if the black hole is 10 to 9 solar masses, to go super Eddington, you have to give 100 solar masses per year, which is a lot.
If not, let's thank Marta one more time. So you gave luminosities of the other black holes. You said things like 10 to 36, 10 to
Yes.
39. So those are in our own
On top
galaxy.
of my
Those,
head.
but those are not so faint. Right?
Well, as I said, I can show you the plot of this. Well, you have to know where to look at, though.
So, but, so at 10 to 36, 10 to 39, you can actually survey with X-rays the whole galaxy.
Yeah. If you're sure that they don't get mixed up with the X-ray boundary.
So you get mixed up a little bit, but at least you can know where they are. You can, so maybe you don't know. And so, and you, I remember